Hey, welcome back. So Lewis says that a covalent bond comes from the sharing of two electrons between two atoms, and it's actually the valence electrons that are responsible. So we're going to really focus on the valence electrons. And if you remember from the last chapter we looked at, the group number, that is the number 1A through 8A above the element on the periodic table, is almost always equal to the number of valence electrons. And there's just one exception, and that exception is helium. Helium, although it's in group 8, it actually only has two valence electrons. In fact, it's element number 2, so it actually has 2 protons and 2 electrons. It couldn't possibly have 8. So just as a reminder, here's our periodic table here. So all these elements here have got 1 outer electron. All these elements here in group 2, the alkaline earth, have 2. And then the transition metals we're going to ignore for now. So all these in group 3A have 3, 4, 5, 6, 7, and all of these have 8, apart from helium at the top here. So helium, in some periodic tables, is actually placed above there because it has the same number of valence electrons as these, but it's inert, it's unreactive, so it's got a full outer shell, so it has more in common with these noble gases here. So it's funny because sometimes you'll see hydrogen written here, sometimes you'll see it written here. And sometimes you'll see helium written here, or sometimes they just float above. So these first two elements don't really fit in very nicely anywhere. So let's try and draw some Lewis structures. So what Lewis says is to focus on the valence electrons. And so Lewis says each valence electron you represent as a single dot. And if we've got something like hydrogen, so hydrogen has got 1 valence electron, it's in group 1, we just write a single dot. If we look to the element underneath of it, lithium has got 1 valence electron, so we just write a single dot. So if we move over to group 2A, then we've got beryllium. Beryllium is 2 valence electrons, and underneath it, I believe, is magnesium. And so we got 2, and I guess just to keep it neat, under lithium is our friend sodium. And when we skip the transition metals, right, and go to group 3A, so we're keeping with the main group here. And at the top of group 3A, we've got boron, and underneath it, we've got aluminum. So we just put 3 dots around there like so. And let's see, group 4A, top of that is carbon. So I'll just do, I'll do silicon as well. We just talked about it. So they've got 4 valence electrons. So we put 4 dots around it, something like that. So there we go. What we normally do actually is after we get to group 4A, we're halfway through the periodic table, and the convention is to pair up once we get halfway through. So when we go to nitrogen, we've got 5 electrons, and the convention is to take the first 4 and leave them unpaired. That is to say, they're on opposing sides, and they're not hanging out next to something else. And then the 5th one, we pair up, and I'm going to put it something like that. And if we go to group 6A, oxygen, and actually let's do 7A and 8A, why not? Oxygen's at the top of 6A, so 1, 2, 3, 4, we're halfway there. 5, 6, there we go, so they're paired up. And 7A, we got fluorine, so it's in group 7, so we got 7 valence electrons, 1, 2, 3, 4, and then we start pairing up, so 5, 6, 7, something like that. And then we've got neon in group 8, and so the first 4 go by themselves, the next 4 pair up, and so we have something that looks like that. And if you were to write helium, so you might think, well, helium's in group 8, so it's got 8 valence electrons. Actually, it's only got 2, and but the outer shell is completely full at that point. And because half of 2 is 1, so the first electron's written unpaired, and then once we get after the first half of the shell, the other ones are paired up. So helium is conventionally written with a pair of dots like that. Honestly, it doesn't really matter at all. And why does it not really matter? Well, these are noble gases. They're completely inert. They don't react with anything. So we really almost never worry about the Lewis electron dot structures, to be honest, of these isolated atoms. But what's interesting, I think, is that those atoms on the far right-hand side, so underneath neon is argon, they're very, very stable. And the stability comes from the fact that they've got a complete full outer shell. And so we'll see something called the octet rule in the next little bit of material. And the octet rule basically says that these atoms are going to try and get 8 electrons to make them very stable. And there is a duet rule. And the duet rule says that some atoms will only want 2 electrons to be stable. And we'll see that hydrogen lusts after a second electron. But helium, we can see, is a noble gas that already has that full outer shell with 2 electrons. So we'll apply the duet rule to hydrogen, essentially. Helium already has it, but everything else on the periodic table is going to be an octet rule. So everything's going to want to look like group 8, those noble gases on the end. Okay, so here's a challenge for you. So maybe you can take a couple of elements and draw the Lewis dot structure. So here is selenium. Selenium is an extremely stinky element. And oh, how about something like phosphorus and maybe something like calcium. So go ahead and pause the video and draw the electron dot structures, the Lewis structures. Okay, so if you've unpaused, you should find each one of these on the periodic table. So selenium is in group 6A, phosphorus is in group 5A, calcium is in group 2A, and so that tells you the number of dots to write around them. And I'll do this in blue for fun. So calcium, you've got 1 dot, 2 dot. Selenium, right, you've got 6 electrons, you're in group 6, so 1, 2, 3, 4. After that, we start pairing them up, so 5 and 6. Phosphorus, so the first 4 are unpaired, and then the 5th one is paired. And if you're wondering, how do I know which side to pair them up on? The answer is it doesn't matter at all. So sometimes it looks prettier if you pair them up on opposing sides, maybe even adjacent sides, but there's really no rule that says you have to place them one side or the other.